In this video, I'm going to go over the formal definition of the derivative. And we're going to start out using Desmos as a visual example of the definition of the derivative. So we always start with a secant line. All right, so what do we know about a secant line? And how many places does the secant line intersect the graph of the parabola? Well, we can see here that we have an intersection point around here, and then we have one here. So my secant line is going to intersect my graph in exactly 2 points. All right, so this would be the example of a something we can do without calculus. So this would be a slope, average rate of change. You formally learned this as the difference quotient in pre-calc, and you probably practice problems with the difference quotient. And if we remember from pre-calc, the difference quotient is f of x plus h minus f of x all divided by h. And you did practice problems with that. Okay, so what we're going to do is we're going to expand on from that and see what happens when we apply limits to this. Okay, so let's look at the next part to this. So it says on here, we have a slider. It says this secant has a negative slope. Drag the large blue point to make a secant with a positive slope. Okay, so if we move this point along the curve here, we can see that that secant line slope is changing. Okay, so it's getting smaller and smaller. At this point, it's around 0. And then as we move it farther to the right, we can see we now have a positive slope. So that secant line is changing as we look at different points around that curve, y equals x squared. All right, so what is the secant line slope? Okay, well, we're going to calculate it here. So in this case here, we have our blue line and we want to calculate the slope. So we would take, in this case here, we would have 2.25 minus 1 divided by 1.5 minus 1, which would be 1.25 divided by 0.5, which would equal 2.5. Okay, so our slope here is 2.5. So we're finding the secant line slope, and we're going to see what happens as we get closer to the 0.11. Okay, so in the next example, we have 1.21 minus 1. Okay, so we have 1.21 minus 1 divided by 1.1 minus 1. So we would get 0.21 divided by 0.1, which would equal 2.1. So we can see what's happening here is that now the slope is getting closer to the value of 2. And if we change this into a slider, we can see that as we move that blue point down, that slope is getting closer and closer to the value of 2. Okay, and it doesn't matter if we come from the left side or if we come from the right side. All right, so what's happening as we're moving that slider? Well, that's changing the distance between the 2 points we were using for the secant line. That's getting closer and close to 0. So we're actually applying a limit to that. All right. So our definition of the derivative is taking our average rate of change or our difference quotient and applying a limit process to that. All right, so as we're moving this closer and closer, that h value is getting smaller and smaller until I actually change from the secant line slope to the tangent line slope. Okay, so all these would apply here. Okay. All right. So what I'm going to do is I'm going to stop the Desmos video and I will show you some examples of using the definition of the derivative. Okay, so before we do our first example with x squared, let's talk about some terms here. So this part right here, the difference quotient that we learned in pre-calc, this was representing the slope of the secant line. All right, so if we calculated that, that would be a formula for the slope of the secant line. Well, when we apply this limit process, what happens is that slope of the secant line now turns into a formula for the slope of the tangent line. All right, and all of these terms, or these, how we write this out, those all mean derivative. So if we had df of x dx, that means derivative. F prime x means derivative. If it was with y equals equation, it would be y prime or dy dx. Okay, so those are all synonymous with derivative. Another thing is the slope of the secant line is the average rate of change. And the slope of the tangent line is the instantaneous rate of change. Okay, so when you hear the words instantaneous rate of change, we're thinking derivative. Okay, so now that we've learned how we denote that, let's go on and do our first example. All right, to define our derivative, what we're going to do is we're going to take our difference quotient, which is a pre-calc concept, and we're going to apply a limit to it like we showed using Desmos visually. So this is our formal definition of the derivative. All right, so let's find f prime of 1 using the definition of the derivative for f of x is equal to x squared. All right, so what we want to do is we want to take 1, we want to take the limit as h approaches 0, f of 1 plus h minus f of 1 all divided by h. All right, so what we're going to do is f of 1 plus h would be 1 plus h plugged into x squared. All right, so we would get 1 plus h squared minus f of 1. Well, f of 1 is 1, all divided by h, and again, we're taking the limit as h approaches 0. Well, what is 1 plus h squared? Well, that would equal 1 plus 2h plus h squared minus 1 divided by h. Okay. And then what we'll do is we'll simplify the numerator. The ones would cancel out, and we would get 2h plus h squared divided by h. We're going to factor out an h out of the top. So we would get 2h times the quantity 2 plus h divided by h. And then the h's are going to cancel. So we would get the limit as h approaches 0 of 2 plus h, and that answer would come out equal to 2. So in this case here, f prime 1 is equal to a value of 2, which means the slope of the tangent line at the point 1, 1 of x squared has a slope of 2. Okay, so let me show you, we could do this without plugging in 1. We can get the general formula and then plug in 1 after. So let me show you it doing it that way. Okay, let's do the same problem using x squared, but let's just find f prime of x, which would be the general formula for the derivative, and then we'll plug in f prime 1 after. All right, so we would do the same thing. We would take the limit as h approaches 0 of f of x plus h minus f of x divided by h. So that means f of x plus h would be x plus h, and then we're plugging it in for x, so we have to square it, minus f of x, which is just x squared, all divided by h. So that would be x squared plus 2xh plus h squared minus x squared divided by h. So the x squareds are going to cancel, and I would get, let me move down a little bit here. So I would get 2xh plus h squared divided by h. I'm going to factor out an h. So I would get 2x, h times 2x plus h divided by h. Now I want to apply the limit process to this, the limit as h approaches 0. So my answer in this case here would be f prime x as h approaches 0. By direct substitution, we just plug in 0 for h, we would get 2x. So what that means is that the derivative of f of x equals x squared is f prime x, which equals, in this case here, 2x. So the value of the slope is going to depend on what the x value is. So in this case here, we wanted f prime 1. We would plug in 1. We would get 2. So let's say we wanted f prime of 0. Well, f prime 0, we would plug in 0 here and we'd get a slope of 0. So that slope is going to change. Tangent line slope changes based on where you're at on the graph. So if I wanted f prime negative 1, if I plugged in negative 1 into the formula for the slope, the derivative, I get negative 2. Okay? So that is a basic example using the definition of the derivative. So let's do a few more examples. All right, let's find the instantaneous rate of change of f of x equal 3x plus 2 at the point 1, 5. Well, instantaneous rate of change is just another name for the derivative. All right, so we're really finding f prime at the point 1. Okay? All right, so let's do our difference quotient with the limit process. So we have f of x plus h. So in this case here, it would 3 times the quantity x plus h plus 2 minus f of x, which would be 3x plus 2, all divided by h. Okay, so we would get, let's move down a little bit. We would get 3x plus 3h plus 2 minus 3x minus 2 divided by h. So our 2's would equal 0, positive 2, negative 2, positive 3x, negative 3x. So I would get 3h over h. So I want the limit as h approaches 0 of this. Well, our h's cancel, and I'm left with the constant 3. So our answer here is f prime of 1 is equal to 3. So now when you think about it, we have a linear equation, 3x plus 2. So in a linear equation, my secant line really is going to be right on top. The tangent line is going to be right on top of the secant line. So in any linear equation, your derivative is always going to equal your slope value in the linear equation. Okay? All right, in our next example, given g of x is equal to x minus x squared, find g prime of x using the definition of the derivative. All right, so in this case here, it's g and not f, but the process would be the same. We're saying the limit as h approaches 0, and we're using g's function now, so g of x plus h minus g of x all divided by h. Okay, so let's do g of x plus h. So that would be x plus h minus x plus h squared minus g of x. So it would be minus x squared all divided by h. Okay. All right, so let's simplify the numerator. So we would get x plus h minus x squared plus 2xh plus h squared minus x plus x squared, all divided by h. Okay, so I'm going to distribute the negative 1, so I get x plus h minus x squared minus 2xh minus h squared minus x plus x squared, all divided by h. Now, if we do this right, we should get some things canceling. All right, so I can see that I have an x and a negative x is going to cancel. I have a negative x squared and a positive x squared that's going to cancel. So I'm left with h minus 2xh minus h squared divided by h. And I can see that in the numerator I can factor out an h. So I get 1 minus 2x minus h, all divided by h. So this is going to boil down to the limit as h approaches 0 of 1 minus 2x minus h. And by direct substitution, if we plug in h equals 0, we're going to get 1 minus 2x. So g prime of x, by the definition of the derivative, is equal to 1 minus 2x. All right, let's try the next example. Given f of x is equal to x cubed, find f prime of x using the definition of the derivative. All right, so we're going to see as this power gets higher, it gets more and more difficult to do the definition of the derivative. All right, so let's try it with this one. So we would get the limit as h approaches 0, and we would get x plus h cubed minus x cubed, all divided by h. Well, x plus h cubed would be the same thing as x plus h times x squared plus 2xh plus h squared, okay, minus my x cubed divided by h. So now we're going to have to distribute this x plus h. So let's go down to the next line here. If I distribute the x, I'm going to get x cubed plus 2x squared h plus x h squared. If I distribute the h, I'm going to get hx squared plus 2x h squared plus h cubed, and then minus my x cubed in the formula. Okay, all divided by h. Okay, so let's combine like terms up here. So my x cubes are gone. So I've got a 2x squared h, and I got a 1x squared h. So that's going to be 3x squared h. And I have a xh squared and a 2xh squared. So that's going to be 3xh squared, and then plus my h cubed divided by h. Okay, so we can factor out an h out of the numerator. So we would get 3x squared plus 3x plus h squared, all divided by h. Okay. Oh, sorry, this would be 3xh for that term there. Okay, so the h is going to cancel. So this is going to boil down to the limit as h approaches 0, and we're going to get 3x squared plus 3xh plus h squared. And if I take the limit as h approaches 0, these terms are going to equal 0. So I'm going to be left with 3x squared. So which means that if f of x is equal to x cubed, f prime x is equal to 3x squared using the definition of the derivative. Okay. As you saw in the last example, even just using x cubed, it's getting more and more difficult to use the definition of the derivative. So for example, if you wanted to find the derivative of x to the 7th using the definition you'd be multiplying x plus h out to the power of 7, which would take forever. So we're going to learn derivative rules so we can bypass the definition of the derivative. Now the question would be, how is the AP going to test you on this? Well, there's not going to be many problems that are similar to this on the AP test, but what they will do is they will try to disguise a derivative as a limit and make sure that you can recognize that this limit is the derivative. So what I'm going to do is I'm going to put a related video up here on how you would use this on the AP test. So it'd be derivatives disguised as limits. Okay, I hope this video was helpful to you. If you liked it, please like and subscribe, and thanks for watching.